Hello everyone, good morning. So today this class about this chapter, we will do today something new. New means we are not going to discuss regarding the topics from the book what's available. For example, we will today this elements, compounds, and mixtures. We will approach this. Our approach towards this chapter will be something in a very new way. Now the question arises, what is the new way? The new way is, this chapter we will be discussing around the approach of this chapter towards, what should I say, towards ourselves, or how can we relate ourselves towards this chapter. Now, obviously, the question arises ourselves and relating this chapter, it's getting confused, or rather confusing, right? Okay, without creating any more, what should I say, or my speeches or this boring stuff, these words, let's get on to this chapter straight away. Then you will understand what's this lecture is, what the new thing all about today's class. All right, so let's start. This is the application. This is the not, I'll say application rather. This is the new thing. The new thing is application of chapter 3. And we all know what the chapter 3 is: elements, compounds, and mixtures. So today's class will be the application of elements, compounds, and mixtures in our daily life. That means we will be applying that one, or rather it is already there, rather we are applying it, we are not aware of that one. Or this can, another perspective is the involvement that we are making of this particular elements and compounds in our day-to-day activities. Either they are getting involved, or we are making the elements, compounds, and mixtures to get involved, or it is already there, we are not aware of that. Okay, so we will today relate, and we will try to discover how this chapter, how these elements, compounds, and mixtures are there, or have been, or are become a very integral part of our day-to-day life activities. Daily life, over here I want to mention about or specify about day-to-day life activities. All right? Okay. So today it will be a very fast, or it's not a fast, but it's an overall recapitulation of the entire chapter. It will be based on elements. It will be based on compounds. We will discuss about mixtures, about separation methods, everything what we have learned so far from the first class till this class, whatever we have learned so far, everything we will be discussing today in a very small nutshell. Okay? We will carry on our discussion as if it's a question answer. So we will go on with a questionnaire, and it will be a question answer session, and we will figure it out that how it is related. All right? The first question comes that if you are interested to make a house of yours, then for better safety purpose, you will go for iron doors at the main entrance rather than wooden doors. So, why? I repeat this question, understand this question very carefully. If you are interested to make a house of yours, then for better safety purpose, you will definitely go for iron doors at the main entrance rather than wooden doors. Why? So let's discuss on this point. Now, what is the primary difference? Because when the context about safety comes, and when two substances are given, iron and wood, then definitely we will be, and this safety, how the safety can be related to iron and wood. Definitely, when it's a context about main entrance, so we will be definitely make sure, or rather making sure, that the entrance should be strong enough and it is not easily breakable. Okay, it is not easily breakable. So the entrance which we are interested in, that entrance shouldn't be easily broken. So the first thing is the wood. We need to compare that iron and wood, who is more stronger. That is, who, brother, who breaks, which one can be, or rather which one is easy to break. It's not that wood is easy to be, or rather easy, can be easily broken, but in comparison, when we are having two substances and we need to compare between those two, then which one can be more easily breakable compared to the another one? So over here, which one do you think is easily breakable, or rather breakable? Well, iron, of course. It's iron. You think iron? Of course, it's iron. We all know that iron is much stronger in comparison to wood. So when we are focusing on safety and iron door safety, then iron doors are more preferable compared to wooden doors, because wooden doors can be is easily breakable compared to iron doors, right? Okay. So what can be that? What's the answer is all about? The tensile strength. So iron is basically an element. We know that it's a metal. So it is an element as well as metal. Whereas wood, it's basically a compound and made up of non-metals. Wood is basically a compound and made up of non-metals. And we know that non-metals, the tensile strength of non-metals is lesser than compared to metals. Remember the difference between metals and non-metals. So the tensile strength of metals is less than, rather, sorry, the tensile strength of wood or non-metals is less than that of metals. So over here, we are having iron doors, which is a metal, and we are having wood, which is a basically made up of non-metals, and the compounds are present. It's basically cellulose. So over for that reason, we are having the non-metals, so their tensile strength will be less or is lesser than compared to that of iron. So it's mentioned over here, the tensile strength of iron is 11 times to that of wood. The tensile strength of iron is 11 times to that of wood. And this makes iron profoundly strong enough to be broken easily. There is one word missing over here. Can you identify what word? Yes. The word is not. There is a small mistake over here. This makes iron profoundly strong enough not to be broken easily. I repeat, this makes iron profoundly strong enough not to be broken easily. So there is one word missing, and what the one word is basically changing the scenario, but there is a point. The point is, on this small mistake uh, is basically, sometimes we also keep certain mistakes, or rather intentionally, to check it out if the students are responding or not. But since it's basically a video lecture, for that reason I'm mentioning over here that I'm declaring this this mistake actually. So iron being having the tensile which is 11 times more, hence it's making the profoundly strong to be not to be broken easily. Clear? So we discussed, so this is one of the application of this chapter. It's metal, non-metals, or elements, compounds, mixtures. Compound has their metal or element is there, the difference is also there. All right. Moving on to the next question, that's aluminium heats up faster than iron, which can lead to food damage during cooking. But still, it is preferred more than iron. Why? Think about it. Aluminium heats up faster than iron. So if I'm having a container of aluminium, a container of iron, then definitely aluminium will heat up faster compared to iron. Now this property will definitely lead to food damage. For which the reason is, for this reason actually we do not use steel containers for cooking. Okay, we do not use steel containers for cooking. We use iron or aluminium. Now much more faster. So why we are preferring aluminium rather than iron? What can be the reason? Okay. The first is compared to aluminium and iron. Iron rusts easily, but aluminium does not rust. The point is aluminium also rusts, but after a certain point of time, the rusting stops. Okay. The difference between rusting of iron and aluminium is aluminium also rusts, iron also rusts, but the rusting of aluminium stops after a certain point of time. So the entire disintegration, the entire decomposition, or the breaking of the transformation of aluminium does not take place. But whatever iron, the entire iron metal, it transforms into rust. It transforms into a different compound. It doesn't remain in any more this metallic iron itself. So there occurs an enormous transformation from the metal to a compound, which leading to the damage or damaging the iron itself. So since it will be used for cooking, so definitely washing is involved. And since washing is involved, then definitely water is involved. And water is one of the primary ingredients which leads to rusting of iron. So iron rusts easily, but aluminium does not. Though a person has to be careful during cooking, but it will save time and money also. So why we are using? Because number one, aluminium does not rust. The first thing. The second, if iron rusts after a certain point of time, we have to throw that particular container or the utensil, the vessel, out. We cannot use it anymore because it is already rusted. So it cannot be used further for a very long time. So under such circumstances, we have to change the iron container. So there is a waste of money as well as there is a waste of time. So time will be wasted if what should I say this iron things are used. So time there is a increased consumption of time with respect to aluminium, and money saving is also there with respect to iron. All right. Okay. So I think this much is clear to everyone. The next question: how sodium chloride is safe and not hazardous? The question is not about poison. The main point about this question is sodium chloride is made up of sodium and chlorine. The elements are itself not safe. They're hazardous. They're deadly. Then how sodium chloride is safe and not hazardous? That's the actual question. So instead of writing such a big question, it's just a small question given that how sodium chloride is safe and not hazardous. The point of approach has to be with respect to this question is sodium and chlorine, the two components of sodium chloride, which are hazardous, which are not safe. So coming to the answer, the components of sodium chloride is sodium and chlorine. The sodium and chlorine both are hazardous. How? Sodium is a very highly reactive metal. It catches fire when it comes in contact with water. So it's a very, very deadly reactive metal. It leads to very vigorous and explosive sort of reactions. What about chlorine? Chlorine is a poisonous gas. So chlorine, though it's a colorful gas, but it's a very poisonous gas. So it's not a very safe one. Now, when these two deadly things are combining together under a certain proportion, they're forming a compound. And that particular compound has totally different properties, totally different features, entirely new, what should I say, behavior. So, sodium chloride is basically a non toxic solid. Sodium chloride is a basically non toxic solid. It is neither it does not catches fire when it comes in contact with water, and it's highly water, though the point is sodium chloride is highly water soluble. It's not having a very shiny or a greenish yellow color. It's having a white crystalline solid, and it's non-toxic also. So complete changeover of properties. That means we know what compounds are. Compounds, they're having different properties with respect to the elements by which it's made of. So chemical reactions occur. They lead to a complete transformation or a changeover of the properties of elements. Moving on to the next question. Calcium is important for our human body. How the calcium of milk is supplied to the body without drinking it. We all know that calcium is very important. Our bones require calcium, our muscles require calcium, our teeth require calcium. So there are lots of places where calcium is necessary. And milk is a very, very good supplier of calcium. It's a very good supplier of calcium. Now, if we will not drink milk, then how this calcium can be transported or can be rather made to enter inside our body? Will not drink milk, then what can be done? Considering milk only. Considering milk only. It's not that, okay, well, since we cannot drink milk, then we will have some other foods. No, this question is not about some other foods. It's all about if you are not drinking milk, then that milk calcium can be transported to our body. How? It's by transformation. Once again, the calcium of milk is converted into calcium lactate or calcium acetate or calcium citrate. All are compounds. Okay, calcium lactate is one compound, calcium acetate is another one, calcium citrate is another one. So whichever one is comfortable, you all are comfortable, any of the compounds you can transform. That means you can make the calcium to leave the milk. You can make the calcium to leave the milk and to leave the liquid or the solution part as solid. I'll leave the system. So this calcium lactate is basically a solid substance. Calcium acetate is also a solid substance, and calcium citrate also a solid substance. So any other one, if we can, now all together is not possible. Either of the one is possible. Either calcium lactate or calcium acetate or calcium citrate. So if we add lactic acid or acetic acid or citric acid is present in lemons. Citric acid is present in lemons. Now, so lactic acid or citric acid or acetic acid, whichever one is comfortable here, if we add that one to milk, then what will happen? The calcium will leave that milk, the liquid portion, and will be precipitated as a solid substance. And we can filter that one, and the solid substance, we can have that as calcium source. It's a very good calcium source. Okay, moving on to the next question. The next question is, list some homogeneous solid liquid mixtures that we prepare in our daily life. List some homogeneous solid liquid mixture that we prepare in our daily life. Can you guess anything? I'm sure you will definitely. So the first thing, solid, cake, sweets. Cake is made up of flour, we add sugar, salt, any other flavors. So when we are adding sugar, salt, and flour is there, then baking powder is there. So all these are solids. But after a certain point of time, what happens is, when after a certain point of time, what happens if we get cake where none of these solids are existing separately? It's totally mixed and they have been blended into that one particular solid in such a fine way that it becomes difficult to identify we can that solid the two solids together differently, or rather distinctly. Well, there only one solid exists, and there's a very good fusion form that is over there. So cake is a solid homogeneous mixture. Sweets, another one, solid. So you're suppose it's made from calcium citrate. So within that we'll add sugar is a solid. Within that we'll add sugar that also get mixed. So it's a very solid mixture. So we can feel that the presence of one particular solid, but distinctly it becomes difficult to identify. The next is solid liquid, salt and water, ORS solution, glucose dissolution, jaggery and water, turmeric and milk. So these are basically solid, homogeneous. Now, with turmeric, on certain occasions, you will find that turmeric is getting beautifully blended with particular within the milk, and sometimes you may also see that some residue of the turmeric also remains. So it depends upon the quantity and it depends upon the quality of the turmeric and how it is mixed within the milk. So for that reason, so based on that, the turmeric actually can get beautifully blended within milk, or sometimes it can leave some residue. Okay, so all these are solid, liquid, homogeneous mixture. Solid, liquid, homogeneous mixture. The next is liquid. Fruit juice and water. Lemonade, we like that lemonade. Flavored syrup and water. Honey and water, etc. So these are, don't you think that all these are part of our daily life? Isn't it? All these are part of our daily life. So can you see that where the mixture is there, solid liquid mixture is there, liquid mixture is there, we are basically we are basically a part of this entire components where we are either using this one with the information or without the information. All right. Okay. The next question: which are the commonly used separating techniques in our daily life? Commonly used separating techniques. One is filtration, sedimentation, and decantation. Now, sedimentation and decantation is basically you should write together because only sedimentation is happening. It's not possible. So decantation, though it's thing that said decantation is removal of that particular liquid or the decant liquid or the supernatant liquid. But I will prefer always that sedimentation. If we are doing sedimentation, then definitely we will do decantation. It's not that we will only do sedimentation or we will only do decantation. Now, for doing decantation, we need to do sedimentation. For doing decantation, we need to do sedimentation because without sedimentation, decantation is impossible. Okay, so decantation and sedimentation, they're basically rather it's a complete process. Hand picking, one technique, gravity separation, centrifugation, distillation. Now, apart from this, if you can relate any other separating techniques with your daily life, or not particularly yours, or within the daily life of others. Now, daily life, this particular thing means daily life. This daily life means there is a meaning. It's not that what we are doing inside lab. So it's not laboratories of school, colleges, or industries. It's basically daily life means our day to day. That means within at home, a normal working scenario at home, and we're probably normally working time. So it's on research labs what we're doing over there. We are going to office and there we are carrying out normal food, having a tiffin and coming back home while moving on the roads and while doing work at home. So these are basically daily life. It's based on the, so my focus is daily life means these particular times. It's not that especially we will do over the research lab. Not only in research, because in research lab all the techniques and more techniques are there. So there is not, it's not a daily life. I'll not focus on that one. That's a daily life. We need to focus on this particular thing. Sorry. Daily life is on research labs. We'll be focused on there. But in day-to-day activities, what we are focusing, that becomes significant. The next question is where the previously mentioned techniques are used in our daily life. Just now we have listed so many of the techniques which we normally use in our day-to-day activities, as we stated. Where? The question now arises where. Let's find it out. The first question is filtration. Tea making, don't we? Don't we filter tea after making tea? The tea leaves and the liquid liquor, we filter that one. So it's filtration. Dirt from tap water. Sometimes we often have noticed that a lot of dirt comes out from a tap water. So what we do, we just turn around, we wrap a cloth around the tap, opening of the tap, and what we see that the clean water is coming there. So what we are doing, filtration, right? Juice from blended fruit. We have seen that many a times that the solid extract comes out and the liquid, because when we're blending fruit, some portion remains solid and some portion liquid. Now we exactly want the juice, the liquid part, not the solid part we are interested. So what we do, we will use a cloth or any other filtering agent or any other net source, anything, and we will just allow that liquid to come out and the solid to stay behind. So what we are doing, we are filtering. The next we are having centrifugation, extracting butter from milk. We discussed this one in the previous classes also. That we normally in home we have noticed that from the milk and from that cream or the layer of fat which we normally preserve in our refrigerators, after a certain point of time, we dissolve that one inside water and we stir it. And after a long process of stirring, after almost about 15, 20 minutes or 30 minutes of stirring, what happens is we see that, and whatever the milk is there inside the cream, it leaves, and only the solid fat comes out. Only the solid cream, the solid butter, those things comes out. And from that butter, we prepare ghee, homemade ghee, beautiful fragrance. Wow. Making cream with a milkshake. We normally have given that one milkshake, we prepare milkshake with the help of mixed grinders, and we have blenders. So when we blend that one after a certain point of time, we see some white foamy like substances are floating in the top. What happens is that is basically the foam of the cream, which separates the milk and it floats to the top. Clothes dryer, washing machines we have discussed. Removing dirt from pulses. Now, this dirt from pulses during cooking, we have seen that our parents must have used. Normally, they use some sort of a stick, and they give a very stirring motion to the particular when that pulses of the dal is going on, it's boiling or cooking, and we see there is a white colored substance that floats out. That's basically some sort of dirt, and they actually then then our parents or mom or dad, whoever, or they used to throw that one out. That's basically, so that particular those dirt and the cream, the foam is not suitable for us to eat. That's another centrifugation. The next, hand picking stones from rice, pulses, husk grains. We discussed that one in villages. Still, it goes on. Distillation, the purification of tap water. Now, the question is, purification of tap water, how that is possible? How that is possible, purification of tap water. We must have noticed that sometimes when anybody is suffering from jaundice, the doctors prescribe please boil the water, cool it, and then filter it and drink it. Now, if we start boiling the water, then definitely the water level will go down. So to prevent that one, what we do is normally when the water boils, we cover that boiling water. So there's a distillation process goes on. That means the water is actually evaporating, it's condensing on the top, and it's coming back again into the container. Now, what we see after the boiling is over, we see white solids are either sedimented or it's precipitated, or sorry, it's there floating at the top of the liquid or liquid water. So one way the salts of the water is out, another way the water, pure water, we have obtained. So that's what we call as distillation. The next question we are having, how the poor thermal conductivity of nonmetals help us in our day-to-day activity? That's a very beautiful question. And if we just think of pure thermal conductivity, that means those substances, that means nonmetals, we all know that nonmetals are having poor thermal conductivity. Now, how are the nonmetals to help us in our day-to-day activities? How that's possible? The first is cooking pan handle covers. We have seen that with cooking pan, the handle covers they are having that made up of either a plastic or any other polythene or nylon, whatever. It's a non-metal, and hence it helps us to hold that one, the pan properly, without feeling the heat. Water heater covers. They are having cover. So, for example, water heater means geysers. The outside is having the plastic cover, so if we can touch it also, we cannot feel that so much of heat. Electric iron handle, we have seen that one. Electric, the base is made up of metal, but the top one is plastic, so we do not feel that heat. Right? Electric wire cover, the plastic cover is there, so we will not feel the heat, as well as the electricity also. Poor thermal conductivity is helping us, right? Isn't it? Moving on to the next question, the dual nature of metalloids is serving as a revolutionary tool in the current and upcoming period. Is serving as a revolutionary tool in the current period and the upcoming period. Explain. What's that? Metalloids, it will serve as a metal and non-metals. So how this property is being utilized? Metalloids are having property of metals, non-metals. This property is enormously exploited by the scientific world to bring the mobile phones, laptop, computers, washing machine, satellites, bulb, and hundreds of electrical gadgets. Hundreds of electrical gadgets. Right? So those electrical gadgets are made up of these particular metalloids, silicon, germanium, the two are very important metalloids are. So it's a revolutionary tool. So the metalloids, they're serving as a revolutionary tool because multiple electronic gadgets are coming into the market and it's making the lives of our very easy, isn't it? The processors, the circuit designing, everything is made up of a particular silicon germanium mostly. We're having the arsenic also, but arsenic is also having its one of the metalloids. It's having some properties of metalloids, though it serves as the poison, but on some contexts it's a very, very beneficial to us. And finally, the last question of today's class, how the property of sharp melting and boiling point of compounds and its information is being seriously utilized. How the property of the compounds are having a property that they're having a very sharp melting and boiling points. How this information is seriously utilized in a daily life. So, how this is? Let's find it out. This information and property has helped people to design several activities which include phase changes. That means if we are having the information at which particular temperature a particular compound will melt, at which particular temperature a particular compound will start to boil, that means it's change of phase, either from a solid to liquid, or it from a liquid to gas, or from a gas back to a liquid, or from a liquid back to solid. So if you're aware of that with this sharp temperature, we are aware that there is a sharp temperature, this particular temperature will only happen, then there's a phase change that's going on, then ice and water vapor formation can be controlled. It means ice formation normally takes place within refrigerators. Water vapor, very easy to form either in containers Or another application is pressure cooker. Application of spirit or alcohol. Application of spirit or alcohol. So this spirit or alcohol also, we know that it's sometimes there is a thermometers which uses alcohol or spirit. We also use this spirit or alcohol during this due to this vaporizing nature. We use that one when in a lot of medical purposes. Uh, so all these, there are a huge number of applications of this spirit and alcohol in our daily life. So nail polish remover and all this stuff for as an sanitizer, it will vaporize. So we do not need to wash our hands each and every time. So if we are having lack of water, so beautiful applications of these particular things will take place if we are aware of the sharp melting and boiling points of compounds. So with this, I will definitely conclude today's class, and I hope that you have enjoyed today's class. And because it's related to your chapter, it's an application-based class today. The lectures are all about the questions. So I hope you can now on you can relate your day-to-day activities with this chapter or with other topics which we will in the upcoming period. So thank you so much. So stay home and take a very good care of yourself. Thank you.